Good morning, everyone. We will be continuing with the air separation lecture, which we discussed last time. And today, of course, the focus will be on the most widely used technology, which is liquefaction of air, which we introduced last time, but we will continue with that today. Few things that you need to remember. One is, of course, that the bulk is nitrogen and oxygen, and as we discussed, there is some amount of argon, roughly about 1%. But these are really the three main components. There are other things which are also present, but their proportions are relatively much less. What you also need to see over here is that the one which has got the lowest boiling point is nitrogen, minus 196 degrees C. And then there is a fairly good boiling point difference between nitrogen and oxygen. Oxygen is a higher boiling substance, minus 183 degrees C, and argon is quite close to oxygen. Okay? So obviously it's not going to be so easy to separate out argon from oxygen, especially since the temperature difference is so low. Okay? So what we'll be really talking about today is the separation of oxygen and nitrogen, and if time permits, we'll also talk about how argon is recovered. Last time we discussed this plot of how if you take these kinds of pressure volume curves at different temperatures, so these are all different isotherms, and this point K is the critical point. So if you go below this point, you start seeing, of course, distinct liquid and vapor phases, and at K is the critical point where the liquid and the vapors are almost indistinguishable. And what we discussed is that to the left of this blue curve is liquid, to the right is vapor, and this is your two-phase region. So these points over here, the dots, are really the critical points. So what you're looking at is a plot which is when you go below the critical point. That's the plot shown here. And so this one is for oxygen, this is for air, this one is for nitrogen, and this one is for argon. Right? So you can see argon and oxygen are quite close together. Nitrogen is on the left side of air. Air, of course, doesn't give you a sharp line. It gives you more like a band. Simply because air is a multi-component system, and therefore their joint properties will come into play. So you get more like a band over here for air. So you can imagine that if you're going from vapor towards, and you're reducing the temperature. This is the temperature axis. This is the pressure axis. If you're reducing the temperature, obviously you will start hitting the two-phase region where you have got both liquid and vapor. And likewise, if you warm up from the liquid, again I'll enter into the two-phase region, which will be liquid and vapor. So that's what these plots are about. One of the things that we will be discussing later on, bear in mind that when you increase the pressure, then the boiling point increases, and when you reduce the pressure, then the boiling point decreases. So many times when we do boil things under vacuum at a lower boiling point, okay, and in a pressure cooker, for example, where you have got something like a 4-bar pressure, so obviously the boiling point of water is higher. And that's the reason why it cooks faster. Okay. So this plot is very important, and just keep this in mind that liquefaction is not just a function of temperature, but that pressure plays a profound role. It's all very easy to say as you lower the temperature. The question is, how do you lower the temperature to this point? It has to be lowered, right? And to something like minus 200 degrees Celsius temperature for nitrogen. So that's a very, very low temperature. And that's where really the Joule-Thomson effect comes in very handy, and the entire liquefaction process is really based on the Joule-Thomson effect. Is anyone familiar with the Joule-Thomson effect?
Sir, I've heard it, but don't remember much.
Don't remember. Okay, okay. It's really the consequence of the fact that gases are real gases, not ideal gases. We did some calculations yesterday, and you saw that the actual pressures can vary quite a bit from the ideal pressures, especially when you go to meaningful temperatures and pressures which you're wanting to study. So that was the effect really that Joule-Thomson, and we are talking about the two masters, Joule and Lord Kelvin, who basically was William Thomson. That these are the two people who discovered this phenomenon, and what they found is that if you were to pressurize gas, a real gas, okay, the only exceptions are hydrogen and helium. And if you pressurize them, when you pressurize, the gases heat up, and the gases heat up because you are bringing them towards the interaction distances, and so when they start interacting, obviously there is a stabilization because they want to interact. And so what it does is that it lowers the internal energy of the system, and the excess energy is given off as heat. And that's the reason why when you compress a gas, it heats up. So then after that, they just used standard chillers to again cool the gas back to ambient or slightly below ambient temperatures. They're in the pressurized state, and then they allowed the gases to expand like a free expansion. And also it is done in a adiabatic manner, so that Q is equal to 0. So effectively what happens is that they were interacting, and when you are expanding, obviously their interactions will cease, which means that the gas will go to a higher energy state because it's lost its stabilization, and therefore you need to do work to pull the gas molecules apart, and that work is being carried out by drawing on the internal energy. Therefore the temperature goes down. So that's effectively what they found. And the temperature can go down sufficiently that the gas can liquefy. Okay, and that's what the Joule-Thomson effect is, which is a liquefaction of compressed gases when they are allowed to expand. They discovered this phenomenon in 1852, and Linde made use of this in separating nitrogen and oxygen around 1904. So about 50 years after the discovery of this phenomenon. So if you have to write down the expression for the Joule-Thomson coefficient, it is basically the change in temperature with change in pressure at constant enthalpy. So that's really what the Joule-Thomson coefficient is. It can also be written in terms of the thermal expansion coefficient and the specific heat, etc. So that's it can be derived. We are not really going to go into those derivations. What you also need to understand is that the change in temperature with pressure is not independent of the temperature and pressure. So there is a relationship. It varies at different temperatures and pressures, and that is given by this particular plot, which you see here. which is you're plotting the Joule-Thomson coefficient, which will have a unit of Kelvin per bar. So Kelvin per bar, that's your Joule-Thomson coefficient, and you're seeing how that coefficient varies at different temperatures. Now, what is very interesting is that you'll see that the Joule-Thomson coefficient, this is 0. It can even be negative. And of course, this part is positive. Now, what is very interesting is that if you take the normal gases, like nitrogen, argon, carbon dioxide, oxygen is not shown, but oxygen, which will be similar to argon, the profile. Okay. Now, all of these typically have a positive value of the Joule-Thomson coefficient at temperatures of interest. When I say temperatures of interest, I'm talking about like, let's say room temperature is around here, 300 Kelvin. So even, if you have got a temperature of around 600 Kelvin, the Joule-Thomson coefficient is positive for these. And as you go lower and lower, the value of the Joule-Thomson coefficient becomes higher and higher. In other words, you'll get more bang for your buck. That even a small change in pressure can lead to a large change in temperature, especially at the lower temperatures. So obviously, if you are trying to maximize the reduction of temperature, actually you will try to do it in a region where I've got a reasonably high value of my mu Jt. Notice also that in the case of helium, only after you have gone to something like maybe about 30 Kelvin, that the Joule-Thomson coefficient becomes positive. And till that point, it's negative. And even for hydrogen, you can see up to 200 Kelvin, the value is negative. It's only after you go past it and go to lower temperatures that the mu Jt becomes positive. Now, why is this significant? Because what is the mu Jt sign got to do with it? It is delta T upon delta P. So if I'm expanding, whenever I'm talking about expansion, my delta P is equal to negative. So if I've got a positive mu Jt, it means that my delta T also must be negative. So that's what will happen with nitrogen, argon, CO2, etc. So delta T negative means that it'll go to a lower temperature when I expand my gas. So I am seeing a reduction in temperature with the expansion of the gas when my mu Jt is positive. In the case of helium and hydrogen, suppose let's say I pressurize it, at some point, let's say around room temperature, and now I let it expand, it's not going to cool because my mu Jt is negative. My delta P is of course negative because I'm doing an expansion. But because mu Jt is negative, my delta T must necessarily be positive. So I will get a heating effect in these gases till such time that I hit a temperature where the mu Jts of these become positive. Whereas in the case of nitrogen, argon, CO2, I don't have to worry because it's got a positive value all the way from around 600 Kelvin onward. So there's a huge difference you can see between helium and hydrogen and nitrogen, argon, CO2. Can anyone tell me why that is the case? I mean, just in terms of your chemical understanding. You see, what happens is that gases like N2O2, the A term, it's a manifestation of the interaction, the stabilizing interaction between the gases as they come together is quite high. Okay? And so it is that which is giving a manifestation in terms of a cooling, because when I'm expanding, I need to do work to pull the molecules apart, and so I get a cooling. Now that kind of a stabilizing interaction, the A term, for helium and hydrogen tend to be relatively very, very low. And if it is going to happen, it will happen at an extremely low temperature. Now, under those conditions, what will happen is that the size effects might become very crucial by bringing them very close together. If let's say I have increased repulsion, then of course when they're expanded, then I will effectively stabilize the system. So what will happen is that by stabilizing is going to a lower temperature and it will release heat. And that's what will happen in the case of hydrogen and helium. So it's really all about fundamentally the A and the B terms, and how they actually affect at different temperatures and pressures. Is everybody clear of this curve and the Joule-Thomson effect? Did you understand it?
Yes, sir.
Okay. By the way, I think it's important also that we understand that a Joule-Thomson effect, we are really talking about the fundamental molecular level interactions in the gaseous state. So a compressed gas is expanded to make it liquid. But we also know that, for example, I can take a liquid, a liquefied gas, and I can vaporize it, in which case I will actually require the latent heat of vaporization. If, for example, I do it under adiabatic conditions, then what will happen is that part of my liquid I may expand. Suppose it's a compressed system, and when I'm putting it through an expansion valve and expanding a part of the liquid, then what will happen is expanding means I'm going from a high pressure system to a lower pressure system. Then to vaporize that liquid, I will have to get the latent heat of vaporization from somewhere. Like for ammonia, for example, it's 23.35 kilojoule per mole. So in vaporizing that ammonia, the rest of my mass must necessarily cool down if I'm doing it under adiabatic conditions. Where else can it draw its Q? So effectively, that's what happens in many of the refrigeration systems, cycles, where I may use a compressor to compress. Let's say, suppose it's an ammonia-based refrigeration, and I've compressed it to something like 6 bar, and I've kept the ammonia as liquid, and then I allow it to expand. So it expands and its pressure goes down, and because of that, the ammonia will boil over. And when it boils, it draws its latent heat from the rest of the liquid, and the rest of the liquid becomes cold. So I can bring down the temperature to maybe something like minus 33 degrees centigrade. And that's how these systems then become refrigerants, and they can extract the heat from, let's say, the space which I want to cool. So that's really the evaporation of a liquid which is becoming vapor, drawing the latent heat from the rest of the liquid, and the rest of the liquid is cooling down. If you look at from a chemical engineer's perspective, what is very important is that when you are doing this kind of liquefaction of the gas, and then of course it will subsequently be fractionally distilled to get the nitrogen and the oxygen in pure form, the energy that you really put in is what energy? What energy did you use in the system? For compression, right? We had to first compress the gas, and then only you can expand it, right?
Yes, sir.
So obviously I have to do work on the system. What will do the compression? It will be some pumps which I will use, which will probably run on power. So obviously the most critical thing that I need to look at is the energy that I am requiring in bringing about the compression. Because once I've compressed, The rest of the things don't require energy. The energy is coming from within the system itself. Obviously, any system must try and minimize the amount of energy input that I need to have to bring about the particular effect. When I'm compressing the gas, I can do it in a single stage, one stage compression, or I can do it in successive stages. In successive stages, I'm incrementally increasing the pressure, and the number of stages is given by n. Now, this is the work that I need to do in n stages. Let's say if I've got n stages in which I'm doing it, n times gamma upon gamma minus 1 RT I, and then the PF upon PI, the final by initial pressure to the power gamma minus 1 upon n gamma minus 1. So this is it. Now, this is lower. The more number of stages I use, for doing the compression, the less work I need to do. Of course, there is also an element of practicality, that how many stages can I possibly use. And what is gamma? Gamma is just the Cp by Cv, and R is Cp minus Cv. And we know that if you have got let's say a monoatomic molecule like argon, it has only 3 degrees of freedom, right? X, Y, and Z directions. So F is equal to 3. So my gamma will be equal to 3 plus 2, 5 upon 3. So for a monoatomic gas. Whereas if I'm talking about, let's say, a diatomic gas like nitrogen and oxygen, my degrees of freedom now, F, is equal to how many? What will be my degree of freedom for a diatomic molecule?
5.
5, absolutely correct. 3 translational like before, and then it can rotate in 2 ways. So there are 2 rotational degrees of freedom. So it's 5. So it will become now 5 plus 2, 7, 7 upon 5. Obviously, you can imagine if I'm taking air and I'm applying this compression, I will have to do it separately for, let's say, argon and for nitrogen and oxygen. But if I'm only worried about nitrogen and oxygen, then my gamma will be always 7 upon 5. Okay? But please do remember that argon will behave differently from nitrogen and oxygen. That's how I'll calculate the total amount of work. What are we actually doing? I can show the work, like effectively what am I doing? I'm doing a compression, but in the process of compressing, what we also found is that the temperature does not remain constant, the temperature rises. So the temperature rise will push you to another isotherm. So if this is my initial isotherm, once the temperature rises, I'll be in a different isotherm. And then if I want to come back here, obviously I have to cool the system so that I draw out all the excess heat, and I bring back the temperature to where it was. And this is my area under the curve, and that's my work done. That is pressure volume, pressure times volume work, which is the area under this curve. Remember that, as I said, you can do it in 2 ways. You can do it in a irreversible manner. At one stage, I do a compression, or I can do it reversibly over multiple stages. And effectively, what that will mean is that the entropy generation will be very different in the 2 cases. If my initial pressure is Pi and my final pressure is PF,
if I do the compression under isothermal reversible conditions,
we know that basically my work is equal to EdV, and then I can express V in terms of RT upon P. Then I can integrate, and I'll get effectively RT ln PF upon PI.
in this particular case, the mechanical work that needs to be carried out is the lowest, and that's why it is written as W ideal. If on the other hand, the compression is done in a single stage, adiabatic compression, then basically there will be a temperature rise as shown in the figure, and the overall work that is done in the single stage will be given by this equation. And basically what you can see is that in this equation n is equal to 1, single stage.
Now, if I do it in a multiple stage, what am I doing? I'm using a compressor, I'm compressing the gas, okay? And then I might be doing a heat exchange to bring it down to the initial temperature, like I showed you, going from here to there. And then what I do is that I repeat the process. I again do a compression. The temperature will go up. Then I can do a cool it down again. And then I continue the process. And so in each stage, as I'm pressurizing, my temperature is rising. I'm reducing the temperature back to the initial state. Again, I'm pressurizing. And I'm just continuing with this process. And finally, I'm reaching again the same point, except that the work that I require to do in this particular case, it will be less than if I do it in a single stage. So obviously, you know, anyone who does a compression will try to do a multi-stage compression, and it will be governed by this equation. You can actually verify it for yourself. So take, let's say, maybe a 5-stage compression, n is equal to 5, and work out the work term, and also try to do it in a single stage, n is equal to 1, and just see what is the difference of the work requirement in the 2 stages. That is the compression part. So this is the work that I need to do. Now comes the question of being able to liquefy it. Only the compressed gas can be liquefied because only the compressed gas can be expanded. Okay, so so effectively, what am I doing? Like, let's say, let's look at the whole system. Suppose, like, let's say I've got a gas which has got an initial state. Okay, the enthalpy and the pressure are defined, and let's say I have now compressed it. So what did I do? I increased the pressure. Okay? And what did we say? That it increases the temperature also, you know, in the system. Okay. Now what am I doing subsequently? I am using, you know, this kind of maybe it could be a water cooling or cooling through a chiller, and I'm then coming down in temperature. But if this reduction in temperature may not be sufficient, so I have to do a further reduction in temperature, and we will see later on how I do that reduction in temperature. You might first just use, let's say, chilled water or even ambient water and cool it down. But later on you'll find that there are certain waste streams which will come out from my Linde process, which will come out cold. And before I discharge them into the atmosphere or into my product, I will obviously utilize its low temperature to cool down my feed stream. So this is what cools it down further. Now I've come to a place where I am ideally poised to do a Joule-Thomson expansion, because this is my liquid state, this is my gas. If I'm doing a Joule-Thomson expansion at constant enthalpy, that's what we said mu Jt by definition is. And so I do that expansion. And so what happens? I have now lowered my pressure because I did an expansion. And because of the liquefaction that took place, you know, it cooled. So effectively, I entered the 2-phase region. So, I mean, this is, of course, the 2-phase as we are showing it, but actually, this is the composite point. But actually, it will just distribute between a liquid phase and a vapor phase. So this is my liquid. What will the liquid be? We will have more of oxygen or nitrogen, which at the higher boiling point between oxygen and nitrogen.
Sir, oxygen.
Oxygen. So in the liquid state, which will be more, oxygen or nitrogen?
Oxygen.
Obviously, the one which has got a higher boiling point, right? Obviously, there will be more of oxygen here, whereas your vapor correspondingly will have less of oxygen compared to the initial, and so it will have more of nitrogen and less of oxygen. So that is one cycle, and I can actually repeat this cycle. Okay, if I want several times, effectively that's how you are getting your cryogenic air separation in a crude way. Is that clear to everyone?
So can you briefly go through this process once again, sir?
Sure. I'm starting with a gas over here. Let's say this is the enthalpy of the system. Now what I'm doing is I'm doing external work and I'm pressurizing it. Now when I pressurize the gas, and it's a real gas, so effectively what happens is that because of the increase in pressure, of course, because I'm doing work, my pressure is increasing, but so will there be an increase in temperature. Why? Because the gases are interacting with each other, and a favorable interaction in which process is releasing heat. So the temperature goes up. That's what is happening. The pressure is going up and the temperature is going up. And that is being manifested in a higher enthalpy of the system. Now what I'm doing is I'm just cooling it with water externally. So I'm reducing the temperature. So I'm bringing down the enthalpy. Now I am also utilizing some cold streams, and I'll describe those cold streams to you. So some cold stream is going past, and so my relatively warm stream gets cold. So it's got cold. So the enthalpy dropped further and it came to this point. At this point, I'm doing a Joule-Thomson expansion, which is delta T upon delta P at constant H, constant enthalpy. If I'm doing a Joule-Thomson expansion, you need not. There are other ways of doing expansion also. I can do isoentropic expansion. So Joule-Thomson is not the only way to expand. But suppose I do it at constant enthalpy, which is this, delta T upon delta P at constant H. Now, because I've cooled the system, because of the expansion, and I did an expansion, so the pressure obviously dropped. I'm coming down in pressure now. And once I've come down in pressure, I enter this two-phase region. This is the typical two-phase region for a gas, like air. We know that at a certain temperature and pressure, which is below the critical point, you will have a two-phase region where you will have liquid and vapor coexisting. That is this point which I'm talking about. And effectively, what is it? It is basically partly things existing as a liquid and partly as a vapor. There's nothing else. Vapor and liquid. My liquid now will have more of oxygen as compared to, let's say, whatever was the oxygen amount initially. Why? Because the boiling point of oxygen is more than the boiling point of nitrogen. And my vapor will relatively have more of nitrogen as compared to my initial gas, because more of the oxygen is in the liquefied form. So effectively here you can see that through this one cycle, I've carried out a crude separation of my nitrogen and oxygen. Is it clear now?
Yes, sir.
Okay. I can show the same thing. Like, let's say initially, suppose I've got 20% oxygen, right, in air, and 80% is nitrogen. And let's say I'm looking at a plot of temperature versus oxygen concentration, and this is my two-phase region. This is what I showed you. What can I do? Suppose I've got only vapors. That is basically this part. And if I've got everything as a liquid, that is this part. Now, what do I have to do? I have to cool down vapors to enter my two-phase region where I'll have some liquid and some gas. And if I'm at liquid, I'll have to warm it up to have some liquid and some gas. The moment I'm here and I hit the vapor state, now my vapor will have much less of oxygen as compared to my 20%. And my liquid will have more oxygen, less nitrogen. This is the part for the liquid. This is the part for the vapor. So effectively, I partitioned my oxygen and nitrogen differently in my liquid and vapor. This is only showing one such process. I can have multiple such processes. I can do it once and then I can repeat the process, where vapors are again condensed, and again the vapor will have less amount of oxygen. Again, I condense it, and I can just repeat the whole process. And finally, what will happen is that I will make my vapor more and more pure in nitrogen, and I'll make my liquid more and more pure in oxygen. And each of these is like one theoretical plate. When we talk about a theoretical plate in distillation, and so the more number of theoretical plates I have, the fractionation will be cleaner and cleaner, and I'll have pure liquid, maybe pure oxygen liquid, and I'll have pure nitrogen vapor. Is it clear to everyone?
Yes, sir.
Okay. So first we talked about compression. That is the work that I have to do and which effectively sets the stage for the subsequent liquefaction, a crude liquefaction into some vapor and some liquid. Then what I have to do is that I have to now more cleanly separate the oxygen and nitrogen, which is done through a standard fractional distillation, except that you're doing a very low temperature fractional distillation. Otherwise, it's the same thing. There's no difference between the two. But because we are talking about relatively low differences in boiling points, so obviously the efficiency with which I do my fractional distillation is extremely important. So what you have in the old days, like when initially Linde was doing his work, what he had was he had these are porous trays. These are trays, and there are numerous such trays through the height of the column. So effectively, what are you doing? At the bottom there is liquid. Liquid is getting heated and becoming vapor, traveling up, and vapors at the top are getting condensed, liquefying, and they are now coming down. So what you are going to be doing is effectively trying to maximize the intimacy of interaction between the vapor, the upcoming vapors of the liquid, and the down condensed liquid. There is a huge amount of work on the interior design of the column, and these are not empty columns. There are hundreds of these trays. These trays are they've got fine pores, so the liquids are falling down from here, the vapors are going up, and it creates a very high surface area for interaction between the liquid and the vapor. Let us try and see what exactly is being done. Effectively, what you do is that first you take your air, you have compressed it a bit, and then you have removed impurities, like for example carbon dioxide, moisture, etc. You remove those. Then you are taking it through a heat exchanger. So outgoing waste gases, which are cold, are helping you to cool up this feed gas, and this is getting warmed up, and this then is going into the bottom of a column, because let's say I have used a cold gas. I may have actually effected a partial liquefaction of the gas, and subsequently what I also do is that I do a Joule-Thomson expansion over here, and the vapors are fed in over here, the liquid comes here, and now I have effectively set up a continuous fractionation process, because oxygen is liquid, oxygen will be at a higher temperature. Any amount of nitrogen which is present along with my liquid oxygen will get vaporized. So my nitrogen will continuously find its way to the top, and my oxygen will get more and more purified at the bottom. Now with this system, Linde was able to achieve pretty good, very pure oxygen, but in about say 65% overall yield. But the nitrogen that he got had about 7 to 10% of oxygen. So it wasn't a very pure nitrogen, so it had to be discarded as waste. So that's what you see over here. After it's done the job of cooling up my incoming feed gas. In the Monday class, we will continue and spend about 15 minutes, and I'll tell you about the subsequent improvement which was carried out by Linde, which led to both pure oxygen and pure nitrogen. Is it all clear? Any questions?
Clear, sir.
Okay.
Thank you, sir.